All right, good morning. So starting a new chapter here today, we are going to be looking at covalent bonds today. And in this chapter, so new chapter, this is chapter 6. So covalent bonds. And starting off with quite a section here, need, have, share, bond. We'll go over that and then look at some polyatomic ions and finally, the resonance structure. So starting off, need, have, share, bond. Let's start with a molecule we're all probably pretty well familiar with, and that's water, H2O. Okay, how need, have, share works is you have to consider how many electrons all atoms need. Oh, thank you.
My neighbor has a business. I buy them and we cannot eat them.
Awesome. Thank you very much. He was this morning. Thanks, Courtney. Well, I think I paused it there, but didn't actually stop recording. Oh, well. All right, so need, have, share, bonds. What we have to consider is all these atoms need 8 electrons. So we take a look at the periodic table. Remember, they're all trying to get over to here. So all atoms need 8 electrons with the exception of hydrogen and helium. Remember, they're on the first valence shell. And there you only need 2 electrons. You have to watch out for hydrogen. We won't have to worry too much about helium because he doesn't bond. Everyone else looking to get 8. Hydrogen needs 2. So hydrogen needs 2. Now there's 2 hydrogens. That little subscript 2 there lets us know there's 2 hydrogens. So 2 for hydrogen, 2 for hydrogen, and then 8 for oxygen. So we add those up and we get a total of 12 electrons are going to be needed. How many do we have? All right, back to our periodic table. From last chapter, hopefully you guys are familiar that everybody here has 1 valence electron, including hydrogen. Everybody in this column has 2. Most of these guys have 2. We're not going to worry about them. There are a couple of exceptions. Hopefully you know the exceptions, but really we don't see these guys in bonds very often. We skip over here to boron and aluminum. They have 3. Carbon, silicon, 4. Nitrogen, phosphorus, 5, 6, 7. And again, these guys are 8, which they have all that they need. So they don't need more. So how many do they have? Well, hydrogen has 1. And remember, there are 2 hydrogens. Oxygen has 6. We have a total of 8 electrons. How many are we going to need to share? Well, we need 12. We have 8. So we subtract to find the difference. We're going to need to share 4 electrons. For bonds, then, so share is 4 electrons. For bonds, there are 2 electrons in each bond. So that we divide that 4 electrons that we need to share by 2, and we get 2 bonds. All right. Next up, we need to choose a central atom. All right, so the least electronegative atom you were in class. You've got one of these charts here that shows electronegativities. So you can hold on to this, you can reference it. You don't need to memorize them. We're going to use this throughout this chapter, so don't lose this little half sheet of paper. So whatever the least electronegative atom is, that's the atom that goes in the center. This is big. Do not make shapes. No triangles, no squares, no circles, no houses, no pentagon, none of that. Do not connect your atoms into a circle. What we do is we choose one central atom. That one central atom goes in the middle, and everything else radiates out from him. So make sure you guys are getting in the habit of that. The only problem is, or the only exceptions are that hydrogen and the halogens can't be central atoms. So the halogens are this family here. They can't be in the middle. Neither can hydrogen be in the middle. So because of that, we really don't need to think about the electronegativities of oxygen and hydrogen because hydrogen cannot be in the middle. So we'll put oxygen in the middle. There's oxygen. And we're going to go ahead and put our two hydrogen atoms around the outside. And then, hey, this always works out. Two bonds, two atoms. That means one bond to each hydrogen. Okay, there we go. These right here. Single bonds. They represent two electrons. There's 1, 2, and 3, 4 right there. So 2 electrons for this hydrogen, he's happy. 2 electrons for that hydrogen, he's happy. Our oxygen in the middle is not yet happy. He needs a total of 8 electrons. He only has 4 electrons. So what are we going to do? To make him happy, we actually add what we call lone pairs of electrons. These are lone pairs of electrons. Awesome. There's oxygen's 8 then. He's got 1, 2 in this bond, 3, 4 in this bond, 5, 6, 7, 8. He's got his 8 valence electrons. He's happy. Another good way to check is to look back up here. We should have a total of 8 electrons in this structure. 1, 2, 3, 4, 5, 6, 7, 8. We've got our 8. There we go. Cool. There's what water looks like. Let's try another example, CH4. So need, again, everybody needs 8. So carbon needs 8, except hydrogen, who only needs 2. We've got 4 of them. That's what the little subscript 4 here tells us. So we need a total of 16 electrons. How many do we have? Carbon. 1, 2, 3, 4. It's in that 4th column over. So he has 4. Each of our hydrogens only has 1. So we have 8. We subtract, or we find the difference between our need and our have. So we're going to need to share 8 electrons. There are 2 electrons per bond. So we're going to have 4 bonds on this structure. Again, normally we'd look at the electronegativities to determine who is the lowest, and they'd be in the middle, but hydrogen just can't be in the middle, so it's going to have to be carbon. All right, so there is carbon. We'll place our hydrogens around the outside, and with 4 bonds, again, it always makes pretty good sense that you can connect them all. 1 bond to each, and there we go. There's methane. Simple as that. Are the hydrogens happy? 2, 2. 2 and 2. So yeah, all my hydrogens are happy. My carbon has 1, 2, 3, 4, 5, 6, 7, 8. So he's happy. There we go. Fantastic. Let's bump it up 1 level here. Let's take a look at the carbon dioxide. Okay, no more hydrogens to play around with. That means everybody here needs 8. So we need a total of 24 electrons. Carbon has 4. Each of my oxygens has 6. Can we find the difference? And that's our share. And then we divide by 2 to get our bond, we're going to have 4 bonds. All right, so no more hydrogen, which means we need to figure out a central atom. The electronegativity of carbon is 2.5. The electronegativity of oxygen is 3.5. Carbon is lower, so he's going to be our central atom. And again, I'll place my oxygens around the outside like that. And now here's kind of the tricky part. We've got 4 bonds. There's 2 of them. What do I do with the other 2? Well, as it turns out, we can make what we call a double bond. So double bonds have 4 electrons. So it's like 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons between these 2 double bonds. So carbon is satisfied. Quick note on double bonds here. They are shorter and stronger than single bonds. Double bonds are. So if we had a carbon and an oxygen that were single bonded down here, they'd be a little bit further apart and it'd be a much easier bond to break. Usually when we talk about how easy something is to break, that talks about a lot of times like the energy needed to break that bond. A double bond is going to be harder. It's going to take more energy to break that double bond. All right, so here's our oxygen. He's not yet happy. He's only got 4 electrons. He needs 2 more. That means 2 lone pairs. There we go. This guy over here, same thing. He needs 4 more. That means 2 lone pairs. Guys, I don't really care where you put them. Now, you can't put your lone pairs on top of a double bond. Like putting them right here, you've already got the bond, and now you're adding a lone pair. Can't do that. Can't do that. But otherwise, put them on top, put them on the side. Don't care. Doesn't matter. Kind of the same thing with up here in oxygen. Had you put a hydrogen going down and then a lone pair up here, absolutely fine. Not a problem at all. All right, so there's our first double bond. Next up, nitrogen. So N2, 2 total nitrogens. Well, they're not hydrogen, so they both need 8. They have 5 and 5, so they have 10. We find the difference. There are 6 electrons that are going to need to be shared, 2 electrons per bond. So we're going to have 3 bonds between these 2 atoms. So because there's only 2 atoms, not really a central atom, they're just going to make a line. Plus they're the same atom, so there's no real difference in electronegativity. So 3 total bonds between just 2 atoms. That's how we draw it. This right here is a triple bond. And this is the shortest. It has 6 electrons in it. So 1, 2, 3, 4, 5, 6. And this is the shortest and strongest of all bonds. So if you read between the lines there, if you're thinking, hey, what about a quadruple bond? There's no such thing. There's no 4. Triple is as big as it gets. So this is the shortest and strongest of all bonds. All right, so this nitrogen here has his 6. He needs 2 more. This nitrogen over here has his 6, but he needs 2 more. There we go. Let's double check. We should have a total of 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everybody's happy. There's nitrogen. Voila. All right, so next up we have polyatomic ions. This is when we have many, poly is many, atoms that make up an ion. So the first one to take a look at is phosphate, PO4 -3. Now, ultimately, we're going to do need, have, share all over again. Nothing much has changed. Phosphate needs 8, and each of my 4 oxygens needs 8. So we've got 5 atoms here that need 8. We need 40 electrons. We have phosphates there in that same category as nitrogen, same family as nitrogen. So it needs 5. Each of my oxygens needs 6. And then here's the catch. That -3, that's how we know it's an ion. That's 3 additional electrons. Electrons have a negative charge, so we've got 3 more of them here. So 5 plus 6 is 11, plus 6 more, 17, 23, 29, 3 is 32 electrons, what we have. We find the difference. So we need to share 8 electrons. So we're going to need 4 bonds in the structure. All right, least electronegative. Here's P, 2.2. Here's O, 3.5. Yeah, P is going to be in the middle there. We'll put our 4 oxygens around. And again, with 4 bonds, just connect each oxygen with 1 bond. Make sure everybody's happy. We got a lot of leftover electrons here. We only use 2, 4, 6, 8. So we've got 24 more electrons. Make sure all of these oxygen are happy. There we go. Let's double check. This oxygen is definitely happy. He's got his 8. He's happy. He's got his 8. 8 and 8. Our phosphorus in the middle, 2, 4, 6, 8. Wonderful. Again, you can always double check. We should have a total of 32 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Sweet. Last thing we need to do, this is an ion. We need to show that charge. So we draw brackets around it, and we add the -3 to show the charge. All right, so another example of a polyatomic ion. I like to do this one because it's got a positive charge. You won't see very many positively charged polyatomic ions, but here's one of them. And so when you do see them, they do something just a little bit different. All right, so nitrogen has, or needs 8, excuse me. Hydrogens, watch out for them. They're oddball, they only need 2 each. So we need 16 electrons. How many do we have? Well, nitrogen has 5. Each of my hydrogens only has 1. And then here's the catch. I know it's a positive charge, but a positive charge actually means you've lost an electron. Electrons are negatively charged. So if you have a positive charge, you have 1 fewer electrons. We actually need to subtract 1 for our +1 charge here. 5, 6, 7, 8, 9 minus 1 is 8. Let's do share first. Take nitrogen, put them in the middle. Hydrogen can't be in the middle. Add our 4 hydrogens around the outside. And again, it's always nice when you've got four atoms around the outside and 4 bonds. It means 1 bond to each. Draw the brackets, put the charge, do not put any lone pairs on these hydrogens. Hydrogens should never, ever get lone pairs. The bond that they make, that's the 2 electrons. They're satisfied. They're happy. They've got their 2 electrons. Nitrogen in the middle here. He's got his 8 electrons. There we go. We're in good shape. And finally, today we're talking about resonance. And actually, this one's easier just to show rather than to do. Start off with SO2. So need, sulfur is actually just below oxygen. There's got the same need as oxygen. Whoops. Well, they all have the same need, except hydrogen. He has the same number. The have is the same, and that's 6. So we're going to need 3 bonds. Take a look at our electronegativity table. Sulfur is 2.5. Oxygen is 3.5. So sulfur is going to go in the middle. Place our oxygens. We've got 2 of them. Place them around the outside there. 3 bonds. Is there any reason why I didn't draw the double bond here and the single bond there? There's 3 bonds. Well, as it turns out, no. There is no reason. In fact, you have to draw them both. So let's first of all make sure everybody's happy here. There's oxygen's 8. Sulfur needs 2 more. So let's get 2, 4, 6, and 8. This oxygen over here needs 4 more. It's got 4 in that double bond. So there we go. But ultimately, there is no difference between this and this. They're the exact same structure. In fact, they're both existing at the same exact time. That double bond is actually flipping back and forth faster than we could possibly see. It's in the same exact time at the same exact place. So what we need to do is draw both. These are both what we call resonance structures. So it's kind of like you're in a valley or in a canyon and you shout and hear your echo resonate, bounces back and forth. So that's what we have happening here. This double bond is bouncing back and forth. So both of these structures exist at the same exact time. And for that reason, we have to draw them both. Double-headed arrow showing that they're constantly flipping back and forth. There is no real double bond here. There is no real single bond. All of these bonds are considered a 1.5 bond. Half the time they have a double bond, half the time they have a single bond. So they're all considered 1.5 bonds. Common test question, I give you a resonance structure and I ask you to compare the bond lengths and strengths. And the idea is there is no difference. They're all the same. It looks like this is a double bond, but really with resonance, it's going back and forth. All right, one last example for you. NO3 -1. They all need 8. It's a total of 32 electrons needed. They have, nitrogen has 5, oxygen has 6, and we have 1 more because of that negative charge there. So we have 24. We're going to need to share 8. There's 2 electrons per bond. So we're going to have 4 bonds here. Nitrogen is my least electronegative. He's lower than oxygen, so he's going in the middle. There's my 4 bonds, 1, 2, 3, 4. Don't forget, it is an ion, so we need to put the brackets around it and a charge outside of it. And then again, we have to notice currently the double bond's right here on the left, but there's nothing stopping it from being up here on top. So we get to draw it again. Double bond on top this time. Double-headed arrow between them because they're flipping back and forth. And then one more time. No reason why that double bond can't be over here on the right as well. So guess what? Once more, we get to draw it. This time with the double bond on the right. -1 charge there. I like to draw them kind of like this, little diamond formation here. That way I can have them all going back and forth and back and forth. You don't have to draw it like this. You have them all in the line or top to bottom. As long as you have one double-headed arrow between each of them, you're fine. And you can see why I like to put them down here. And I can have all of them kind of flipping back and forth. You do have to have those brackets. You do have to have that -1 charge. All of these bonds, not 1.5 this time. Up here, it's 1.5 because it split its time between only 2 places. But now we're splitting our time between 3 places. So these are all considered 1 1/3 bond length. So these are all 1 1/3 bonds. So a little bit stronger than a single bond, a little bit shorter than a single bond, but not as much as a double bond and not even as much as a 1.5 bond. All right, so there's your day 1 notes for covalent bonding. We'll have a few more examples, a few more things to work on, but for right now, you got to go practice. You got some homework. See ya.